All right, let's get right into it. Welcome to this explainer, where we take complex, cutting-edge research and break it down so you can see exactly how it's shaping our future. Today, we're looking at a concept that honestly sounds like pure science fiction, but it is very, very real. We're talking about turning the everyday glass windows in your house, your office, and even your car into invisible power plants.
Now, to really grasp why this is such a game changer, we have to start with a totally mind-boggling number. 1 hour. Just a single hour. I really want you to let that sink in for a second.
Here's why that single hour is absolutely crucial. In just 1 hour, the sun blankets the Earth with enough solar radiation, we're talking about 1.7 times 10 to the 5th terawatts, to supply humanity's entire energy requirement for a full year. The whole shebang. A full year's worth of global energy sits around 25,000 terawatt hours, and the sun delivers that in 60 minutes. So the energy is already right there, literally pouring down on us every single day. Our real challenge as a species isn't finding the energy, right? It's simply figuring out how to capture it without having to cover every square inch of our natural land in heavy, dark solar panels.
So here's our roadmap for today's explainer. 1. The ultimate energy dilemma. 2. Seeing through solar tech. 3. The cost and efficiency reality. And finally, 4. Building cities of tomorrow.
Okay, starting things off with Section 1, the ultimate energy dilemma, balancing space and power.
So here is the massive roadblock we're hitting. On one hand, we've got a rapidly booming global population and a massive, ever-increasing demand for electricity. But on the other hand, we have a strictly limited availability of land. Traditional solar farms are amazing, don't get me wrong, but they're horizontal. They sprawl across vast, vast fields. As we push toward these strict global targets to go 100% renewable, we are quite literally running out of empty, unutilized land to place these massive traditional arrays without disrupting agriculture or natural habitats. We desperately need a way to build up, not just out.
Which brings us to Section 2, Seeing Through Solar Tech and the Science of Invisible Power.
This incredible breakthrough relies on a complex-sounding term, transparent luminescent solar concentrators, or TLSC for short. Back in 2014, researchers at Michigan State University and MIT cracked a massive code. By using organic salts or microscopic materials called quantum dots, they essentially created a surface that absorbs only the light the human eye cannot see, specifically ultraviolet and infrared wavelengths. It's like a bouncer for light. It channels that invisible light to the very edges of the glass, where thin traditional solar cells are waiting to convert it to electricity, all while letting the visible light pass right through to you. It's effectively an invisible power plant.
But wait, the innovation actually doesn't stop there. Enter perovskites. These are crystal structures that are emerging as the absolute rising rock stars of the next-generation solar world. They're lightweight, they're flexible, and they can actually be manufactured at lower temperatures. And what's amazing for windows is that manufacturers can adjust their transparency just by changing the film thickness or leaving microscopic empty sections. Now, it's true that perovskites can degrade a bit faster than traditional silicon, but companies like Oxford PV are brilliantly layering these perovskite crystals right on top of silicon to combine their strengths and massively improve their lifespan.
So, where does this technology actually stand today? Well, fully transparent cells, like the ones pioneered at Michigan State, offer an amazing 86% transparency and can potentially hit up to 10% efficiency. But because they use organic materials, they do currently degrade rather rapidly. On the flip side, commercially viable semi-transparent cells, like the ones from Heliotech in Germany, give you 60% transparency, so they act almost like a tinted window. They offer about a 7.2% efficiency rate, and crucially, they are far more stable for real-world use right now. Plus, think about it. That slightly lower transparency naturally limits the amount of solar heat entering a building, so it acts as built-in climate control.
Let's move into Section 3, the cost and efficiency reality, the economics of solar windows. Because, let's face it, a great invention only changes the world if it makes financial sense.
And the financial reality here completely blew my mind. Traditional solar panels average about $120 per square meter. Fully transparent experimental windows? Yeah, those will set you back about $400 per square meter right now. But look at the middle ground here. Semi-transparent solar windows start at around $80. Since a standard non-solar double-pane building window usually costs between $80 and $150 anyway, these semi-transparent options are already perfectly cost-competitive with regular glass. No way, right? You literally get a power generator for the exact same price as standard construction materials.
The pros here are just massive. This completely solves our initial land dilemma.
Because we're turning building facades into energy generators, they require zero extra land space. These panels also suffer lower conversion efficiency losses when they aren't tilted perfectly at the sun, making them absolutely ideal for vertical, 90-degree installation on massive skyscrapers. They're highly heat-tolerant and incredibly lightweight. Imagine a future where the screen of your smartphone or the sunroof of your car is just subtly charging your battery all day long.
But, we've got to be realistic here and keep things balanced. There are some physical limitations engineers are still battling. The total efficiency is definitely lower. We're talking under 10%, whereas traditional opaque panels can hit around 25%. And because of that lower efficiency, you need a much larger surface area to generate the same amount of electricity, which does increase the cost per generated unit. They also suffer from performance drops during heavy cloud cover, and at the end of the day, they are mostly glass, which brings an inherent fragility to the whole system.
All right, let's wrap this up with Section 4, Building Cities of Tomorrow, looking at the model island.
There's this absolutely fascinating master's thesis by a researcher named Burkhan Aydin that focuses on the potential of building integrated photovoltaics, or BIPV. Instead of just throwing out theories, researchers are meticulously simulating the real-world impact of literally wrapping entire cities in these transparent luminescent solar concentrators.
To prove this actually works, they designed a digital model island populated with 10 diverse building structures, everything from residential complexes to large commercial towers. Next, using MATLAB, they calculated exactly how much solar radiation a panel sitting at a strict 90-degree vertical angle would actually capture. They adjusted for the fact that it isn't tilted perfectly toward the sun like a traditional roof panel. Finally, they calculated the internal population of these buildings and matched that vertical energy generation directly against the residents' daily consumption to see if a skyscraper could truly power itself.
And to see if this could be scaled up globally, researchers also looked at historical financial trends. By mapping the massive historic price drop of traditional monocrystalline solar cells from 1975 all the way to 2020, analysts can project a similar financial trajectory for these transparent concentrators. The data projects that this technology will become radically affordable and highly efficient right on time for our critical global energy targets. Specifically, milestones aiming for a 32% sustainable energy share by 2030 and a 100% share by 2050.
Which brings us to the core takeaway of this entire explainer, beautifully summarized in this quote from the research. Instead of constructing new renewable technologies in land areas that are limited, using TLSC on buildings would result in compensating the rising electricity demand. We can absolutely meet the massive energy demands of our booming population. We just have to be smart enough to transform the existing vertical footprints of our cities, rather than sacrificing more of the natural world.
So the science is here, the economics are rapidly aligning, and the simulations prove that it works. So I'll leave you with this provocative thought to ponder today. As this tech scales, when will your very own living room window become your personal power plant? Thanks so much for joining me on this explainer. Keep your curiosity sharp, and I'll catch you in the next one.